The next Dragon cargo ship headed to the International Space Station with thousands of pounds of provisions for crew members and experiment supplies is coming to the International Space Station on April 8th. It also is including a first of its kind experimental module, an expandable capsule that will be attached to the station for a 2-year period. And today, joining me to talk about the Bigelow Expandable Activity Module, or the BEAM, is Rajib Dasgupta, the International Space Station Research Integration Manager and the Project Manager for BEAM. Rajib, thanks for being with us today.
Good morning.
So why don't we start off, if you can give us a quick history of expandable modules and where Bigelow fits into that story.
First of all, thank you for giving me the opportunity to come and talk about this exciting beam project. NASA actually started looking at expandable technology in the early 1990s as part of the Transap project, and that work went on for about a few years, 5 or 6 years. Then in the early 2000s, Congress actually canceled the project due to funding problems, and then all of that work was documented in a US patent. At that point, Bigelow Aerospace purchased that patent from NASA and started developing commercial inflatables. And between 2006 and 2007, Bigelow Aerospace actually launched two expandable modules called Genesis 1 and Genesis 2. Both of them were successful, but the thing to be noted is that none of them were human rated, but their performance from a leak standpoint and structural standpoint were very good. So this went on in the mid 2000s. Now, in 2013, Bigelow Aerospace gave NASA a proposal to launch a human rated small expandable module to the International Space Station just to prove the technology for future deep space applications. So that is the short history of expandables and its association with NASA.
Excellent. So this expandable module is made out of a very different type of material than we're used to. We're used to these
Right.
metal modules.
Right.
So can you tell me about the similarities and differences in the strength and protection of the Bigelow module?
Expandable modules actually from a strength standpoint gives equal or better protection than metal modules. Just to give you a point of reference, for expandable modules, because they are made of non-metallic soft goods materials, the safety factors we have to certify these materials to is much higher than comparable metal structure. So from a unit weight standpoint, just the primary structure of the expandable happens to be lighter if you compare per unit weight. But if you add all the other protective layers like the MMOD and the external MLI, we don't really see that much of a weight benefit. The main benefit of expandables is in the launch volume, because you can pack the expandable to a tighter volume and then expand it in space. Now, in the case of beam, it expands to 4 times its packed launch volume. So that's a considerable advantage from a launch standpoint. And from a protection, we also look at protection from orbital debris, MMOD, micrometeoroid and orbital debris. And the beam module has been tested and proven to be equal or better than equivalent metallic modules.
Wow.
Yes.
So then what are the overall goals of this demonstration for the beam being attached to the International Space Station for 2 years?
The first and foremost goal is to obviously prove the expandable technology with a human rated spacecraft like ISS, and we call it increase its technology readiness level, something called TRL, to 9, which is a flight demonstration. So that's the first and foremost objective of it. And then some of the other main objectives are to test its long-term performance from a leak standpoint, to characterize the radiation environment inside the module, to also characterize the thermal conditions inside the module and the air quality. So those are the main objectives of the beam demonstration. And we have a suite of sensors, which I can describe later, to collect all of these data inside the beam module.
So then what will happen whenever beam is attached? Describe how it's going to be deployed once it's attached to the Tranquility module.
Okay, so I'll start off from Dragon launch, if you don't mind. So Dragon launches, as you know, Falcon 9 launches with the Dragon spacecraft on April 8th. And in 48 hours or around 2 days, it berths to the to nadir docking berthing port of space station, right? And then 5 days later, after Dragon berths, 5 days later, we are going to use the space station's robotic arm, which is called the SSRMS, to extract the beam module from the Dragon's unpressurized trunk, translate the arm, and berth it to the Node 3 aft port. Okay. So once berthed, the module will stay in that condition till the end of May. At that point, we plan to deploy and inflate it. Okay. And there is a lot of preparations that goes on as part of the inflation process. After the, once it's berthed, the crew has to first pressurize the vestibule, which is the section between the beam and the Node 3. That's the vestibule section. So they have to first pressurize that, prepare the vestibule for the deployment. In other words, set up the deployment controller, make the electrical connections and all that. And then once all of that is done, then the crew starts in expanding the beam module first with ISS air through a tiny port and a valve called the NPEV valve. Okay, so we use ISS air to inflate beam to its full shape and a pressure of about zero point 0.4 psi. Once that is done, then the crew through the controller releases the air from the 8 inflation tanks from beam, and that air pressurizes the beam module from 0.4 psi to roughly about 14.7 psi to equalize the pressure with ISS. So once that is done, beam is fully inflated, then the crew does a 80-hour leak check. We want to make sure that the module is not leaking due to transportation, handling, and other conditions, which we don't expect, but just in case. After the leak check is done, the crew then goes in, uh, prepares the vestibule ducting to start the airflow inside the module, and does first ingress, takes the air sample for safety reasons. Then once we are sure the air is clean and habitable, then the crew gets in first ingress and then starts the airflow. That's how the operation goes, basically.
So it's going to be inflated in late May, and they have to go through all of these checks and balances.
Right.
But it'll stay there for 2 years. So
Right.
what's going to happen during that 2-year period?
So we are going to, during the 2-year period, we're going to collect all of that technology data that I just talked about. So we have 2 radiation sensors called the REM and the RAM passive badges. With both those 2 of those sensors, is going to characterize the radiation environment inside beam. And actually, we have those identical 2 sensors in the metallic part of space station, all the other modules. So what that'll enable us to do is compare the radiation environment inside beam with the radiation environment inside space station. So that'll be a very important piece of data. Then the other sensor we have is called the deployment dynamics sensor. That is actually going to use at the time of deployment to measure the dynamic loads that are generated during the deployment. And the third sensor is called the DID sensor, and the function of the DID sensor is to measure any MMOD particle impacts on the outer surface of beam. And then we also have the last one is the temperature sensor that measures the thermal environment inside beam. So in the 2 years span, we are going to get all of this data. Okay, so it's going to be valuable data for us to study the expandable technology demonstration on ISS. And also we'll have the on-orbit crew ingress beam uh, around 2 to 3 times every 6-month increment, and check the surface condition of the module, get surface and air microbial samples, and then change out these radiation badges, the RAM badges, because they need to be changed out from time to time and sent to the Earth for analysis. So this is the overall kind of plan for the next 2 years, and hopefully it'll give us some very good data.
A lot of data
A lot
to
of data,
collect.
yes.
And you have 2 years to do it, and we hope to see some really good results
Yes.
from that. So then after the 2-year period, what happens to beam?
After the 2-year period, because space station program needs to use that port for other purposes, we have to jettison beam, dispose beam by the robotic jettison method. So the Space station arm again goes and grapples beam through the aft side grapple fixtures, and then takes it to the nadir, extreme nadir position of space station and releases it for jettison and uncontrolled reentry. And we have done all our analysis to show that it'll take about less than a year for that jettisoned object to come and reach the Earth. So that's how it's going to be disposed after 2 years.
Wow.
Yeah.
So 2-year period, a lot of data to collect. We are very much looking forward to
Yes.
its launch on April 8th. The crew is going to grapple it on April 10th. Rajib, I'd like to thank you for being with us today. We are very excited for the launch and to see all this data that's going to be coming in over a 2-year period. Rajib Dasgupta, International Space Station Research Integration Manager and the Project Manager for BEAM. Thank you.
Thank you.